Okay, as per your request today, I am going to talk about 14.40 question in a little bit more specific in detail. So the question actually have two switches. As I mentioned, that usually the switch has to be in sync. So you can see that at time t equal to 0 and time t is equal to 0, the switch is simultaneously flip. And so in this case, this switch is actually turning this circuit off from the entire circuit, and actually this switch is actually connecting this system into part of the 1 ohm as part of one system. So as I mentioned before, you have to consider two periods of time. One period of time is when t is less than 0, so which means that in this case, this switch is going to stay there for a long time, so I use this as a red color here. This is the inductor as a result of having a long time charge, which become a short circuit. Same thing for capacitors, it will be an open circuit. So our point of interest is actually finding the voltage output across that capacitor here. So you see that V output as a function of in the time domain. This is what we're going to find out, and this picture can be further simplified more. So you can see it in the next figure. Is actually a more cleaner and simplified version. So you have 10 volt connecting a resistor in parallel with another 2 ohm resistor. So this is simply a voltage divider problem. So you have 10 ohms multiplied by the ratio of 2 divided by 3, that give you 6.67 volt. Now so we consider that as one part that we know of the voltage that has an initial value on those capacitors. So the next consideration is to decide when t is greater than 0. So which means that, as you can see from this picture, is that when t is greater than 0, then this switch is open, and then you connect this switch back to the system. So the green and the blue color indicate that there is a two subsystem. So actually the main power is actually isolate from the source now. So the only thing that you have to consider here is this green arrow part of the circuit. And for modeling the capacitor that has initial value, we're going to insert that voltage source here. So the 6.67 volt we found before, you're going to divide by S because of the Laplace transform for that constant, and converting all the frequency information from the j omega. So you have this S times 1 would actually equal to S, because you only have 1 Henry for the inductors. For the capacitors, is 1 over S times C. In this case, C is also 1 farad. So you have that 1 over S. So this is the part of the system that you will have to consider for the analysis. So again, there are many different ways to solve a circuit problem. With the calculator that you have now, you can actually decide what way you want to do to make it simple. What I usually do is to simplify the equivalent circuit here. So if you can see that this is a little bit slightly next page, you have 1 ohms, 1 ohm, 2 plus S, that is in parallel, and then you have the voltage source in series with the capacitor. So I write it in this way. And what I found here is that I can actually simplify this Thevenin into a Norton, so that it will make it as a 3 parallel impedance information. So converting this part into this, you have a current source, and then in parallel with 1 over S, which is here. And the 6.67 divided S actually becomes 6.67 because when we do the conversion, you have to use I, which is a voltage current source, equal to V over Z. And that V is actually 6.67 divided by S, that's the V, divided by the impedance for that capacitor, that give you 1 over S. So when you have this equivalent circuit, it's more intuitive now. You have 3 individual impedance, which you can compress them into a single equivalent as Z equal to 1 over S plus 1 over 2 plus S 1 plus 1 over 1 ohms, and then you invert the entire thing as minus 1. So this is the equivalent circuit for impedance you learned before from circuit 1. So if you do that by plugging in into the calculator will handle it and output to the way that is organized enough for you to see that. So this is a number you will see from your TI-89 calculator: s plus 2 divided by s squared plus 3s plus 3. So this is a z that we had. The question is to find out the voltage across that. What will be the voltage for that? So in order to do that, you have the current source, and then you have the impedance information, which is s plus 2 over s squared plus 3s plus 3. This is a part of the impedance. To convert it back to the voltage, which is a Thevenin equivalent circuit, you basically need to use this multiplied by that to find the voltage, which is the thing that we are interested in, and that gives you 6.67 times s plus 2 over s squared plus 3s plus 3. So the final step what we have now is actually, as you can see, I actually already do this complex factors. This is the same as what we have in this situation, except that I factor them, and apparently this is a repeated complex root. So to do that, you have to write k1 over s plus this root, and then plus k1 conjugate of the other one. So I have to make this complete. This wasn't complete enough. So once you get to this point and find out what would be k would be, eventually this is 3.85 with the angle minus 30 degree, and that is the, if you use your calculator to output it as a polar form, this should be something you're looking for. And then I talked about this before for the other classes, that you can organize this in the way that, remember the cosine of the Euler form with the reorganization that give you a 2 here, and then 3.85 is multiplied by 2, and then e to the power minus 3 over 2 times t. That's actually coming from the real part of that, multiplied by cosine of the imaginary part of it, which is a square root of 3 over 2 times t minus 30 degree of this. And then if you copy the whole thing here and multiply the 2 times 3.85, that gives you 7.7. And this is the final solution to 14.40 question. Hope this helped.